Okay, thanks everyone for coming to the 2DCC webinar today. Our speaker is Dr. Chinedu Ikuma from Lehigh University. And Chinedu, you are good to share your screen and get started as soon as you are ready.
Well, thank you, Kesley, and thanks to Stephanie for inviting me. Can you guys hear me okay?
Yes.
Perfect. Okay. I'm going to begin momentarily. All right. So today I'll be sharing with you some works that we've been doing in trying to design a kind of new generation of advanced materials, which involves integrating 2D van der Waals materials with organic molecules. Just to give a quick acknowledgement, some of my students, my group is made up of currently four students and a postdoc, and I do have some key collaborators, basically some of the collaborators that have participated in some of the works that I will share with you, specifically my experimental collaborators from U.S. Army Research Lab, UC Davis, and the Worcester Polytechnic Institute, who are basically experimentalists focused on advanced material synthesis and characterization. And also Srivanis Ragaranja, who is here at Lehigh, who collaborates with me on a kind of high throughput pipeline. These works are generously funded by NSF and Department of Energy. Kind of an outline, just to guide me through some of the things I'll be sharing with you. Specifically, some motivations, which is basically looking for energy efficient materials. I will introduce some concepts of organic, inorganic interfaces, data-driven design of these new materials. Then I will share with you some of the materials that we've computationally synthesized that have been fabricated by some of our experimental collaborators. So they are not just hypothetical systems, but some of them have actually been made and shown to have some of the properties that we predicted that they do have. Then I'm going to summarize, kind of just reiterating what I've shared with you. All right. The motivation basically is to increase the efficiency or accelerate the discovery of new materials and also facilitate materials with targeted properties. Think about if you want to make a new material, there are 1,001 choices from, because the parameter space is too large. Experimentally, that would be a lot to do, but computationally, we should be able to narrow down the parameter space and make life easier for experimentalists. It generally reduces costs and the number of experiments while also mitigating risk. It kind of brings into perspective the convergence of science, folks from computer science, folks from material science, physics and chemistry, and other related sciences. It's generally very, but over years, we've kind of been relearning some of the tools. This is trying to do some of the computational, data-driven solutions, leveraging some computer skills. And also key motivation is addressing sustainability. New materials generally kind of have more enhanced properties that we hope could contribute to eco-friendly materials, thereby enhancing societal relevance of materials. I don't know the makeup, but I'm guessing that there are some students in our mix. So just to give an overview of what experiment, computing, and theory is all about. Basically, theory focuses on developing models, hypotheses, predictions, and conclusion. Experiment does some measurements, observations like observable, collecting data, and testing the hypothesis predicted by experiment. There has been this third tier, which kind of simulates these models, tests these hypotheses, observations, and also visualize. I always call computation as experimental version of theory. All of them are kind of needs each other to survive in a way. If you want to do some experiment, you need computation to validate some of your observations most of the times, and the computation needs theory to be able to do the computing. But I always say data and the material informatics is like the glue. So what I will call the fourth paradigm, which is big data driven sciences, which uses data from theory, experiment, and simulation. So you can look at the evolution, the first paradigm, second paradigm, and third paradigm, which is how far we've gone. Each of all these paradigms kind of rubs off each other. So this is the era of big data where we need data-driven solutions to be able to make informed decisions. All right, so that kind of wraps some initial motivation. I will share with you what I mean by inorganic and organic hybrids, and how what we are looking at, the type of material synthesis we are embarking on, is generally different from the state of the art. So basically, you have an inorganic layer with some either 2D or quasi 3D structure that is stacked like this. These interfaces is very, I would say, exotic, because many physics could be engineered here, and they are generally more easier to tune. Tunability is the key when we want to design new materials. So these organic and inorganic hybrid interfaces generally exhibit some novel physics, not all the time, but in our high throughput design, we end up running into a few that showed some optimized properties. As you can see here, this is pristine P3H3, and when you design the organic and organic molecule interface with MOS2, you can see enhanced optical absorption within this important wavelength. This is near infrared and visible light, where photoactivity could be generally enhanced. Also, as you can see, when we have this hybrid system, we generally can drive the mobility to orders of magnitude larger than either of them staying apart. So generally, when we have these interfaces, we do have materials with enhanced and improved properties that we can easily tune. Because of their nature, they have these large area surfaces, which could be optimized for photocatalysis and solar cell absorption. It has, because of that, it will have a highlight absorption. There is tons of structural tunability that we can engineer, and new properties generally emerge. Synthesis-wise, speaking with some of my experimental collaborators, they have said that these materials are generally very easy to synthesize, and using various approaches from chemical epitaxy to pyrolysis to electrospray method, chemical intercalation, electrochemical intercalation, and the rest of them are some of the many routes that we can easily grow this hybrid structure. So design-wise or experimental design-wise, we have lots of ways to be able to grow them, because one issue with new material is that they are generally hard to make, limiting their potential applicability because we can't grow them in large scale. So, but in these organic and inorganic hybrids, they are generally easy to grow using well-established approaches. As I already showed, this is kind of tying it to maybe neuromorphic application like synapses, axons, and dendrites, which are like biological concepts when we talk about potential applications. And this is the IV characteristics of these hybrid structures that generally have efficient feed effect transistors that could be also enhanced, optimized for diversity of application beyond what we currently could achieve with conventional materials. Now, comparable to the state of the art, the way we design our materials is kind of different. If I go back here, these are just like two interfaces. What we are saying is, let's go a little bit further. This is a particular, I'm trying to get my cursor to show up. Hopefully, okay, there it is. This is the state of the art. We take these van der Waals systems, 2D van der Waals systems. A typical example is this transition metal dichalcogenide. MOS2 is like their poster child. We can take something like lithium, sodium, and intercalate between these layers. Now, there is something also unique. These layers are, these gaps between these layers are intrinsic, meaning they occur naturally in these van der Waals systems is of order of 3 Armstrong. So we can literally insert some molecules, ions in between those gaps that we can use as a tuning parameter. Another beautiful thing about chemical or electrochemical intercalation is that they are reversible, unlike generic approaches that are not reversible. We can insert and also remove these molecules or ions within these natural van der Waals gaps. There are many ways. You have, this is a couple of ways that we can do the intercalation. It can be by electrolyte, electrochemical, either chemical, or a scenario whereby you put the intercalant and the host between a sealed environment and run some temperature gradient across them that makes them to mix naturally. Now, what we are saying is, instead of putting lithium, sodium, or elements between these natural occurring van der Waals gaps, we can put molecules. Specifically, we've been interested in conjugated molecules, small conjugated molecules, and organometallic molecules. So we can put it in between these layers. Again, I'm looking for my mouse. There it is. And you should be able to tune their properties. This is a snapshot of some of our high throughput screening where we can systematically tune the electronic band gap of MOS2 using various various conjugated molecules. Again, these are small conjugated molecules of order of 30 atoms per molecule. And this is also a snapshot where we put something like thiophene between two, this is MOS2 and this is tungsten disulfide. And this is SNS. So this is like the transition metal dichalcogenide, and these are like the transition metal monochalcogenide, something like GES, CSNS, and the rest of them. And we can even go a little further by taking ring-like structures. This particular example are the so-called metallocins. The metallocins has ferrocin, cobalt-ocin, chromocin, and the rest of them. And we can insert them either vertically or horizontally within these natural van der Waals gaps. And that also gives us another length to further tune the properties of the material. I'm kind of just showing you the type of materials that we're generally interested in, mainly all the whole 2D structures, and these are some of them. We've also been looking at perovskites, and not just only oxygen. We also look at chalcogens like chlorine, iodine, or bromine, replacing oxygen in these ABC3-like structures, and a couple of other complex perovskite-derived structures that I will share with you. One interesting thing about all this class of materials is that correlation is everywhere. Aside from natural quantum confinement that we have in 2D structures, these materials, even at their bulk level, already have some intrinsic strong electron-electron interaction that we can further use to engineer the property of the system. They do have diverse application, from catalysis to optoelectronics, spintronics, ion transport, biomedical or biomedicine, energy harvesting and storage are some of the potential applications of these kind or class of materials already at their niche level. So we can further improve or enhance their properties. And as experience have shown, both experiment and computation, 2D structures on their own might not be enough to give us some of the properties that are intrinsic at the atomic limit. So we need to do something else, which is either stacking them as a heterostructure and further intercalating them using ions, molecules, or any other intercalate. Looking at the periodic table, these are some of the materials we're interested in. The group 4 chalcogens, the chalcogens themselves, group 3 chalcogens, transition metal chalcogens, and the rest of them. As I already pointed out, these class of materials have diverse properties that covers literally all the whole electromagnetic spectrum, from very low bandgap systems like boron phosphide to very large bandgap system like hexagonal boron nitride, or maybe just say from graphene, which is semi-metallic, to hexagonal boron nitride, which is a large bandgap material of order of 6 electron volt. At their heterostructure, they do have already very interesting properties that we can further enhance by intercalating these molecules or ions or elements within their natural occurring van der Waals gap. Now, how do we design this type of materials? As I already pointed out, the compositional and configurational space of all these class of materials are so huge that a Dissonian approaches like we normally do before is not an option. We can't use traditional way that we generally design materials to design new materials, especially at this third or fourth revolution, as I shared with you earlier on, where data, aside from where data kind of drives some of most of our decisions, both in businesses and in science. So we need to find an efficient way to do that. So I will share with you some of the approaches that we use to design these new materials. Now, in a potential high throughput material screening, we have a bunch of building blocks that leads up to large candidate space. This is the complete configuration space. Now we do screen them. We screen them and we look for some hints, like which of them has energy gap of more, maybe 1 EV. We select them and we test. We do further testing by doing some high-level calculations, either at the level of screen, Coulomb, and Green's function method, or hybrid functional like HSC or the rest of them, or doing other things, maybe matching them with experiment, as I will share with you later on at the level of multi-fidelity modeling. Then we get some target materials that we can also now tell our experimental collaborators to see whether they will see anything based on what we've predicted. Now, this is a typical example where we start with 10 to power 6 complete database. We can apply machine learning to predict some properties and use quantum chemistry simulation like density functional theory to further narrow it. Then expert selection and maybe synthesis and testing, kind of feedback loop to look at some of these properties. At the end, we just have like 10 core materials that we can select and do some more rigorous testing, synthesis, and characterization to see how their properties emerge. So this is kind of an overview of a typical high throughput and also high throughput plus said machine learning could be used to accelerate that process. Now, in actual machine learning process, we have labeled data. So once we have a labeled data, we use supervised learning. When we have an unlabeled data, we like, is it metallic or insulator or semiconductor? This would be like a true or false at the unlabeled side. At the labeled side could be, does this material has a band gap and what is the number? So when you have a continuous data set, we use labeled data. When we have kind of true or false like scenario, we normally use unlabeled data. So this is unsupervised machine learning, while this end will be supervised machine learning. And a typical workflow for this will be feature generation or feature engineering, data splitting, that is you split your data into two, you keep some for testing, you keep some for training, you do some validation split for that, then you train, you hold out. These are like holder that you use to do some evaluation, like right here, you validate this. So this is an internal loop. Then once it converges, you use your holder data to do some evaluation. So this holder split could be referred to as unseen data set, which are those data sets that we keep aside that our machine learning algorithm didn't see. That is, they are not part of our overall machine learning algorithm. At the end, we get an optimized model that we can use to do prediction outside the training and testing data set that we've already designed. In our case, it's a little bit complicated because we have many things that we need to carefully optimize. So we have an intrinsic active learning embedded inside the machine learning, and there's also a multi-fidelity modeling. I'll try to explain each of this a little bit. At the active learning level, we are using transfer learning, coupled with multi-fidelity, which is a kind of bootstrap-like approach that we do exploration and exploitation. I'm going to share with you how bootstrapping is done. And there's kind of experimental feedback with some of our experimental collaborators, and we can learn some information from what they told us, and we feed it back and keep doing iterating the process until we get some top candidates. These top candidates, based on our design, we say top 50, we'll do some further high-level calculations using something like density functional perturbation theory for the phonon spectra and Raman spectra, GW for the electronic, and we also could do something like a beta Sapeti equation, because technically 2D materials are strongly correlated, and because they are strongly correlated, electron-electron interaction is not a small parameter. So we need a way or a theory that could account for that. That is where this multi-fidelity modeling comes in. So multi-fidelity modeling, in essence, is simply you have this huge data set, which are low fidelity, calculated as, say, density functional theory using local and semi-local functional, like local density approximation. Then at the other end, we have these high fidelity data, either from experiment or GW, but they are small. So we can do is a transfer learning that kind of makes this low-level data set to be at the same accuracy level as this our high fidelity data. So there is an inner loop that we use to do that, and I will share with you down the line how we can use that to actually optimize the band gap of the material, because for optoelectronic application, which is what we are generally interested in scenarios like this, the electronic band gap is the most essential parameter. So in the language of machine learning, the band gap would be like our target. All right. So in our case, this is kind of an example of one of the structures or how we do it. So we have a building block. So this building block is coming from PubChem. We can directly query the PubChem and get the type of molecules that are of interest. Specifically for this design, we are interested in conjugated molecules. We can also put some other constraint, planarity, and limit the number of atoms in the molecule, say to 30 for computational feasibility, because if the molecule is too large, it becomes generally an NP-hard problem because we still need to do a GW calculation and the beta-Sabatier equation. We need to still solve that, which is highly memory intensive, that if the size of the molecule is too large, we generally won't be able to simulate it. So with that, we form plausible intercalated 2D structures. We do some mechanical calculation using our internally developed toolkit, LS2, to tell us whether they are mechanical stable. And once we do that, we generate library of material properties. This is where we apply a multi-fidelity machine learning model, which involves going beyond standard ab initio calculations, in terms of density functional theory. For this particular case, we have a computational framework focusing on transition metal chalcogenides. For this, we have generally 24 TMCs at their homogeneous bilayer level. We chose this based on phase and stability. On the organic molecule, based on our screening, because we put some constraint, the size, the planarity, it has to be planar, as you can see here. We obtain roughly 14,000 planar molecules. So technically, we need to do 336,000 simulations. But as I already pointed out, these are doing such large, many number of calculations is unfeasible. And what we did is we made a computational framework that kind of scans through this using our algorithm. There is an inherent multi-fidelity modeling, data-driven solution, high throughput screening within our pipeline that kind of looks at these materials. Here we are using the intercalation energy as our target. So the intercalation energy is a measure of how easy it is to insert or remove atom, ion, or molecules within this natural van der Waals gap. So if it is negative, it's generally, we refer to that as being spontaneous intercalation. If it is positive but is small, that is still okay. But if it is positive and large, then such materials will be generally hard to grow or synthesize under normal experimental conditions. You might need some catalysis or something like that to speed up the reaction. So we generally won't focus on those type of materials. So we use the intercalation energy to screen and get a library or collection of stable structures that will further build machine learning algorithm on to understand their properties. Now, as I already pointed out, we have 336,000 hybrid materials that we need to do simulations on. Instead of performing DFT calculations for all this, we generally start with a randomly selected set of 500 systems. And what this entails is we use this bootstrap method, which is nothing but a Bayesian optimization method in mathematical language. So we build surrogate models. So these surrogate models involve resampling technique, meaning you remove with replacement in our whole data set. As simple as it may sound, the bootstrap technique makes no assumption about the data distribution. So it is highly a very well systematic statistical method to get an insight about the distribution of any large data set. So technically, we do this resampling technique 5 times for our case. So we start with 500 randomly selected hybrid structures. We perform DFT-like calculations on all those guys and calculate their intercalation energy. So generally, what I'm showing here is the number of, sorry, this place is cut. So this is the percentage of the number of most stable structures. So within our randomly selected bootstrap method, we do first, where is my cursor? the first, second, third, fourth, at the fifth SCF level. Again, this SCF is in the language of the bootstrapping. All the home materials that are involved in the fourth iteration are already in the fifth iteration. So this is what we use as kind of our convergence criteria. Our target is identify 50 top most stable structures from our compositional space. Once this happens, we stop. That is the 50 top most structures that we want, and they are the most stable within our 336,000 hybrid structures. As you can see, technically, instead of doing 336,000 calculations, you roughly do about 2,000 or 2,500 independent DFT calculation, which is like a fraction of doing this. And being that the bootstrapping technique makes no prior assumption about the data distribution, we are able to capture the overall trend with respect to which of the structures that are stable or not. Also, within the internal bootstrapping method, we can further engineer the process of exploration and exploitation by using a neural network. One of the way to do that is, I talked about this low fidelity data and high fidelity data. So here we have a bunch of DFT band gap, and here we have very few GW experimental band gap. We can use this multi-fidelity transfer and active learning approach to make this low-level data or low-fidelity data to be at the same accuracy level as these guys by using a multi-fidelity model. Just to give you an insight of what is the major difference between traditional machine learning and transfer learning. In traditional machine learning, we have an isolated single task learning. So knowledge is not retained or accumulated. So there is no knowledge transfer. In transfer learning, learning of a new task generally relies on on previous learned task. So the learning process can be faster, more accurate, and or need less training data set. So this transfer learning approach is generally more accurate, more scalable, and more predictive than traditional ML model. So what I'm showing you here is a typical example of some kind of transfer learning approach where we can make the PBE data. The PBE data here is a Purdue book Eisenhower, which is a semi-local functional within the density functional theory. As you can see, these are the band gap that they predicted. While for MGO, ZNO here, I just took diversity of materials that have large, small, and intermediate band gap to show the trend. Then the red one is the experimental data. As you can see, within our transfer learning, we are literally kind of hitting the experimental data. This is within 3 to 5% of experiment, and that is good because that is where the experimental error bar is. So we can use this transfer learning to not only train our data set, but make our low-level data set to be very accurate to enable us make more informed decisions. We can also do multi-targeting property where we can both at the same time predict the mechanical and the electronic structure at the same time using the work function to color code it. So this is like the another way we can further screen these materials to simultaneously get optoelectronic materials that are at least mechanically stable. That is a good step. So we have an in-house tool that we recently released, both that can do mechanical and elastic property calculations of 1, 2, and 3D systems. So if you do have some time, check it out and see if it could be useful for any of your research. All right, now I've shared with you some ways that we try to narrow down the parameter space to enable us make some, get some material with promising properties. And by the way, I'm not seeing anybody. If you do have a question so far, I know there is 15 minutes for questions, but you can interject and ask questions if you can't wait till the end. I'll be more than happy to attempt them. So what I want to spend my remaining 20 minutes or so is to share with you some of the materials that we've been able to computationally synthesize and some that have been experimentally fabricated, and share with you some of their results and their properties. One thing that we are interested in our research is neuromorphic materials, which is materials that could be tailored to make information processing and storage faster in general. So-called neuromorphic is simply means brain-like. So the brain is the fastest supercomputer known to man. The brain has roughly 10 to power 11 neurons that have 10 to power 15 connections. Just look at this massive stuff. Just look at this. Now, perhaps the crucial component for memory and computation in brain is the synapses. You'll be hearing about synapses, which is a potential solution to do this is to design system with dynamical reconfigurability, that is system that could easily change their behavior by just simple change in their local environment. So biological intelligence generally use CMOS elements. We call it swap prohibited. So I won't go into details of this, but just to tell you that one synapse is equal to one memory store, and one neuron is equal to two memory store. That is kind of one-to-one equivalent of how we can, when we are trying to make this transition. So one synapse generally requires 50 transistors and multiple passive elements. So a typical neuron generally will require 10 to power 6 transistors. That is a lot. So technically, our silicon-based CMOS-based, silicon-based CMOS might not be the best approach, even though silicon still remains the grandfather when it comes to semiconducting materials. We might need to look beyond that if we want to make this transition. All right, so some background definitions. Can the brain computing devices based on materials, concepts, and systems, could we make it such that this could perform at the level of the brain? So if so, what are the basic research challenges and material science question that we need to address this? Why neuromorphic? Generally, computers have become essential to all aspects of our life. All of us, even now, some of us might be looking at our phone. Those things need where to store the data, Internet of a Thing, interconnectivity, and all those stuff are the reason why we need more efficient materials. Just to put it out there, about 5 to 15% of the world's energy is spent in some form of data manipulation and processing. 2D materials, because of the advance in scaling down and flexibility, are aiding this novel route to creating advanced quantum materials. I think I have some few more, about 10 minutes. Please remind me when I have 5 minutes so that I don't go over time. I don't know, just remind me. So as I already pointed out, our current computer architecture uses bits, zeros and one. The human brain is like an analog version of computer, meaning it uses, I talked about synapses. In terms of biological concept is synaptic weight. That is what it uses during decision making and learning. So the analog nature and the neural network's massive parallelism is the reason why the brain, with roughly 20 watt, are much better at complex task pattern recognition than even the most powerful computer. So look, 1 megawatt versus 20 watt. Just do the math and see the type of energy that we consume in our high performance environment. So what we envision is a system or a material that could emulate the human brain with the computational hardware that could give us these massive neurons that we could scale up to make information processing, data storage, and all sorts not faster, more efficient, and the rest. In actual device design, this is one way you can stack them. And for our own particular application, we have layered materials. We can put lithium, sodium. As I showed you earlier on, instead of putting lithium, sodium, or elements in general, we are putting molecules to further drive these systems. Now, for a particular example here, this is hafnium disulfide. COP2 here is a particular type of metallocene known as cobalt-ocene, and CrCp2 is a chromocene. This is their electronic band structure. As you can see, they are semiconductor. And this is their kind of their work function, both for the parent system and the interconnected structures. Now, this is an experiment. Experiment kind of quantified what we saw experimentally, that electrochemical interconnection leads to band gap narrowing. This is supported by large charge transfer from the molecule to the host system. And this is the actual material where they have been, where it has been made. And this is kind of a schematic of how the structure looks like. Now, what we saw in this material is that you can both reintercolate and deintercolate. I talked about this before. You can insert and remove those molecules. And this is a cross-plane conductance showing this hysteresis-like behavior where you can both introduce the molecule and also remove the molecule. So conductivity modulation via proximatized effects normally at their interfaces. This is the optical micrograph. But the most important observation in this material is the enhancement of this cross-planar transport by almost 400-fold, as you can see here. And this signature is a signature of dynamical reconfigurability, which is well sought after for neuromorphic application. So that is why we tag this system as materials for brain-like application. And this was covered by various scientific media when we first published this in Materials Today. Just to add, I think we are the first group to show the intercolation of molecules in 2D van der Waals systems. So hopefully it becomes a research niche where others could start looking at some of all these problems. So what I'm showing you here is another generation of new materials that we've been able to computationally synthesize in our group. And this is what we call all inorganic derived 2D halide perovskites. So it's CS3Bi2I9. As you can see here, these materials are characterized by flat bands. This is their structure. They have high spin-orbit coupling, that is strong spin-orbit coupling, and the relatively manageable exciton effective mass. What we saw in this material is that even though it is quite flexible, because of their small elastic constant Young modulus and the rest of them, comparable to 2D, other 2D systems like MOS2 that have 150 or 300 nanometer Young modulus. This is like 8, so it's orders of magnitude smaller. So it's quite flexible, but it has a huge optoelectronic, electrophotonic behavior, especially within the important EM, that is electromagnetic wave spectrum of visible light and near infrared, where photocatalysis and absorption are always generally of importance for photovoltaic or solar cell applications. We further also show that we can tune these materials using strain. So what I'm showing here is, this is the strain. As we increase the strain, it does, because it's pretty very flexible. The strain above 10 for compression and 15 for tensile generally kind of leads to mechanical instability in the system. We did also carry out some other high throughput material screening of related family, and we did share the whole CIF file and information of all this material. We didn't really study these ones in detail, but we just kind of try to demonstrate which of them is mechanically stable and could be further screened for potential application. We recently started doing some substitution, isoelectronic substitution in these materials, and we are seeing something even more interesting. This material have one of the highest exciton binding energy ever known by other materials. It's almost 2.5 EV. I mean 2.5, sorry. The binding energy is almost of order of 2.5, which is one of the largest, if not the largest, known for any 2D systems out there. Now, we also looked at other type of group 4 monochalcogenide, and our interest in this is GES and SNS, for example, are very good photovoltaic materials. But for us, when we started screening these materials, they showed very interesting properties that is kind of in line with what Louis and Matty proposed in language of intermediate band systems that are theorized to have power conversion efficiency of up to 63%, that kind of navigates beyond this quasi-Shockley limit of 32%. Generally, for any intermediate systems, Anderson Mott limit is required to engineer intermediate band state. And what does this mean? It means highly doped system with strong interaction combined together. So heavy doping, but this heavy doping generally leads to more non-radioactive recombination, which are known to destroy potential photovoltaic application due to recombination effect that quenches radioactive recombination. So what we saw in this material is copper intercalation in GES, either GESE or with their heterostructure or their homostructure, could be used to engineer a typical type of intermediate band systems that is kind of slightly different from what we know, because they are not heavily doped. They are strongly correlated, but they are not heavily doped. So our particular material, as you can see here, their energy band, that is their sub-band gap, low level, high level, and their intrinsic band gap are in line with what Louis and Matty had initially proposed as to be the optimized band gap regime for materials that could be used as an intermediate band systems. Now, but that is not the end of the story. This material is also not generic. What I'm showing here is the electronic density of state calculated with semi-local and non-local, local and semi-local density functionals. As you can see, the intermediate band gap is only revealed when we turn on many-body interaction. So what we also say here is that this material is driven by many-body interaction, and which is a signature of strongly correlated system. So in our material design, we have achieved an intermediate band system without heavy doping, and that is also strongly correlated naturally, because quantum confinement in 2D structure generally engineers a strong electron interaction. We also did a high-level exciton spectral analysis of this guy. And what we are showing here is this intermediate band gap. which shows like sp3 like hybridization between the low laying the carcogen sulfur that are within the proximity of the copper.
5 minutes left.
Perfect. We're almost there. Thank you. Now, when we first computationally synthesize this material, we asked some of our experimental collaborators to do some measurement to see if they're able to see it. So this is an ultra-fast terahertz measurements done by our experimental collaborators from Worcester Polytechnic Institute and UC Davis that shows that indeed, if you do these careful measurements and the terahertz regime, you can capture these intermediate band states, and they show that this is the normalized photo current, and this is the time delay, kind of the lifetime of those excitonic states within the intrinsic band gap of our material. So kind of a confirmatory experiment that shows that these computationally synthesized materials could indeed be made in the lab in experimental setting. We also went a step further to see if we can learn anything about their potential application as a PV, as a photovoltaic systems. So what we did is we constructed a solar cell array where we use this, our new material, as an active layer. So what I'm showing here is the photo current generation, and this is the absorption of the various layers, and this is the optimized external quantum efficiency of our material. As you can see, the external quantum efficiency is more than 190%. I've been asked this question, why is it more than 190%? Should be 100. Here, these are multi-exciton generated systems that could, in essence, be shown to exceed 100% in these type of materials. But another important thing that we are showing is that at this important energy or frequency regime or wavelength regime, these our active layer is independent of thickness. Remember, our active layer technically is at the extreme limit of one couple of nanometer or Armstrong. So what we demonstrated here is that at least, even though it converges as a function of thickness, these low energy regime or wavelength regime where light absorption is highest, it generally does not depend much on thickness. All right, so I think that takes me very close to my time. So I will summarize by saying that I've shared with you some machine learning and advanced machine learning methods that we are using to computationally synthesize what I will call new generation of quantum materials. I shared with you some examples based on hafnium disulfide intercalated with metallocene, where we observe dynamical reconfigurability that are appealing for brain-like applications. I also shared with you an all inorganic derived perovskite, where we observe giant electrophotonic response that could be exploited for PVCs and valentronic applications, even though I didn't highlight about potential application for valentronics, but at least for PVC applications. I also shared with you some recent computational observation that we've made that we are quantified by experimental collaborators, where we observe many body-induced intermediate band states. Again, the uniqueness of this is there is no heavy doping in this system, so non-radiative recombination is generally reduced. This type of material is also very appealing for advanced PVC applications. All right, and that will be it. Thank you so much for your time, and I'll be more than happy to attempt some of your questions.
Thank you. Are there any questions? Questions? It doesn't look like we have questions, so thank you so much for your time. I'm going to go ahead and stop the recording.
Okay, perfect.